In this video, we'll do a 2D simulation in Harold to model facet heating due to optical absorption and surface recombination. If I open the simulator, it's set up for a two-dimensional simulation. Two-dimensional in this case means in the vertical direction and also the longitudinal direction, i.e. the cavity axis. So that's all set up correctly. I click the Start button. And once this is finished, I click the Inspect button to view the results. In the versus bias result, we can look at the optical power at the second facet, for example. And also we can look at the active region temperature. And if we wanted these on the same graph, I can just highlight both of them, use the arrow to slide them over into the multiple plots box, and then click. And I can view them on the same graph. And you can notice in this graph that the lasing threshold is around 5 amps. And that's quite large, but that's because this is a 4,000 micron wide laser cavity. I can remove these from the multiple box. I can plot other factors such as the power, the various power contributions. And actually, let's plot them on the same y-axis. And we can see the various power contributions there. Okay. Now, because this is a 2D simulation, we can plot 2D results. So I go to the 2D results tab. Let's look at the thermal, and let's plot the temperature. But I'm going to set the resolution on the z-axis to be 600, and click OK. So what we have here on this axis here is the cavity axis, and then this axis here is the epitaxial layer axis, where most of it is the substrate. But you can see here that at the end of the cavity, at the second facet, the temperature is around 46.5 or thereabouts. So there's no real significant increase in temperature at this facet. And notice there's various right-click options from the chart. I'm going to click Plot Cross-Section. I'm going to set to plot in the vertical direction at a position at the center of the cavity, let's say which is 300. Click OK. And actually, just to zoom in a little bit, let's edit these axes as well. Can edit the x-axis to be -10 to +10. The quantum wells are located at 3.4, around about here, so there's no significant temperature increase that we can see here in the center. And if we repeat this for the end of the cavity at z equals 600, we're going to see a very similar graph. So let's switch this up and include the effects of optical absorption at one of the facets. And we do this by editing the properties of the facet in the cavity node. So you notice at the top here, this is where we've decided to simulate the cavity called no facet heating, which is this one here. Let's edit the properties of cavity absorption at facets. And the difference between the two, this is no facet heating. On the right mirror, there's no absorption. On the absorption cavity settings, we have a small amount of absorption. So to switch over to simulate this, in this video we'll do a 2D simulation in Harold to model facet heating due to optical absorption and surface recombination. And when the simulation is finished, we'll click the Inspect button and we'll plot the 2D results of the temperature in the cavity, again with a resolution of 600 in the Z direction. Now we can see now in the top right corner there's a significant temperature increase. And if we plot the cross-section, so the horizontal cross-section at y equals 3.416, which is the center of the active region, we can see there's definitely a very sharp rise in temperature close to the mirror due to the optical absorption. If we plot the cross-section in the vertical direction at z equals 300 and 600, we can see a definite difference as well. Vertical 300. And vertical 600. You can see it's a very different effect. Again, due to that 3% of optical absorption at that right facet. Okay, so we have a third cavity already set up for us, where we've reduced the absorption back to 0. But in this case, on the right mirror, we have set a surface trap density of 5e to the 15 centimeter per centimeter cubed to model the surface recombination. So we're going to go back to the simulator and switch over to this one now and start the calculation. And when the simulation is completed, we click the Inspect button and we'll repeat the steps from earlier. So we'll look at the temperature on the 2D graph. And again, we see a similar temperature increase in the top right corner. If we want to plot the cross-section, horizontal 3.416. Again, this is the center of the active region. We can see a sharp temperature increase from, around about 43 degrees, up to 60 degrees at the right facet. Again, we can compare the center line with the right facet. So again, plot cross-section, vertical at 300. Okay. Again, remember the quantum well is around about here. Compare that to at the location of the right facet, where we see inside the active region there is a massive sharp temperature increase, which can affect the lasing of the device.